let's begin our study of second-order linear homogeneous differential equations with constant coefficients. In other words, differential equations of this form, where x of t is the unknown function, and I'm not writing of t here, but there's all time dependence here, and where a, b, and c are constants. So as a quick reminder of what this giant mouthful of words is referring to, second order, it's a second order differential equation. Linear, the left-hand side is a linear operator being applied to x. So that means linear combinations of solutions to this differential equation are solutions. Homogeneous, that just means the right-hand side here is 0. Specifically, the right-hand side is 0 after you get it into this form where the left side is a linear operator being applied to x. So homogeneous refers to this 0 that you see here once you write the differential equation in a certain form. And constant coefficients refers to the fact that a, b, and c are constants. They do not depend on time. So they are just some numbers. And we're not specifying what they are so that we can be completely general about everything. All right, so what's the method? How do we solve these? With separable differential equations, I gave you a method, right? Separate, then integrate. With linear differential equations, first order linear differential equations, I gave you a method, which was the method of integrating factors. So what's the method here? There's going to be a method. And at first, the method is not very satisfying, but go with it and see how far it can take us with solving this problem in general. So the method is to make a guess. This is what you will do every time when you solve one of these kinds of differential equations that have this form, is you will make a guess, and it will always be the same guess. You will guess, let me write the of t, you will make a guess that there is a solution of the form e to the something times t. So make this guess every time. When you make this guess, you will find multiple solutions, hopefully. Multiple solutions of this form. And then because this differential equation is linear, it has the feature that taking linear combinations of solutions, like number times solution plus number times another solution plus number times another solution and so on, a linear combination like you would for taking linear combinations of vectors. Because this differential equation is linear, taking linear combinations of solutions is a way to generate more solutions. So this kind of guess is our method for finding basic solutions, of which we will take linear combinations afterwards. Okay, so when we make a guess of this form, the lambda is unknown, right? That's why it's a guess. We'd like to see what conditions lambda has to satisfy in order for this guess to be a solution, if there are any conditions. Maybe the guess is always a solution. Maybe the guess is never a solution. Maybe it's just a bad guess. It'll turn out the guess is sometimes a solution, depending on lambda. So we'll get some requirement placed on lambda. Okay, so now we put in the guess. Put in guess and see what demands are placed on lambda, what lambda must do. Okay, so in order to put in the guess, I need to know, let me just write the differential equation down. This is what must hold in order for this guess to be a solution. I need a times the second time derivative of this, so I'll write that here, plus b times the first time derivative of this, x prime, so I'll write that here, plus c times this, so I'll write that here, equals 0. So this is what I need. Okay, now let me go in and compute derivatives. What's the derivative with respect to t of this? It's lambda e to the lambda t. And then what's the second derivative, x prime prime? It's the derivative with respect to t of this. Another lambda comes down, right? So it's lambda squared e to the lambda t. Okay, so if e to the lambda t is to be a solution to the differential equation, then this equation must hold. And in fact, not just if, but if and only if. So this equation's holding is exactly what's needed for e to the lambda t to be a solution to the differential equation. Okay, so if it turns out the equation never holds, then our guess was bad. But it will turn out that there's always a way to make the equation hold. So the first thing to notice is that there's an overall factor of e to the lambda t being multiplied by everything, right? So you can pull it out. It's e to the lambda t times a lambda squared plus b lambda plus c. And this is why it's such a good guess, because you can pull out the e to the lambda t and then totally get rid of e to the lambda t. Because look, we're demanding that this non-zero function of t times this constant be 0. And we're demanding that this be true for all t. In fact, if it's true for any t at all, then it must be that this part is 0, right? Non-zero times something equals 0 implies that the something must be 0. So you can get rid of this. Or if you like, we're dividing both sides by e to the lambda t. And then 0 divided by e to the lambda t is 0. So we find ourselves here. And look at that. It's a quadratic polynomial in lambda. So we expect there to be probably maybe 2 solutions, 2 lambdas that make this true. And each of those 2 lambdas would generate for us a solution. So this will have 2 roots, and each lambda that makes this true, will have the feature that e to that lambda times t will be a solution to this differential equation. Okay, so I'm trying to be completely general, and that's why I'm not putting in actual numbers for a, b, and c. I'm trying to give you the general technique. But at this point, different things can happen depending on what the numbers are. Because when you have a quadratic polynomial, different things can happen, right? Like, if I plot if you plot a quadratic, so here I'm plotting against a lambda, I'm plotting the function a lambda squared plus b lambda plus c. It's a quadratic. Well, if a is positive or negative, that determines whether it's flipped like that or like that, right? And depending on the values of a, b, and c, you could have a situation like this, maybe, or like this, where there are 2 roots, 2 values of lambda that make it 0. Or you could have a situation like this, or maybe like this, where there are no roots, so there's no values of lambda that make it 0. Or you could have a situation like this, where it just barely touches, and there's just the 1 root. There's 1 value of lambda, or people call it repeated roots. So this ends up being a square. All right, so those are 3 different situations. Three possibilities from here, depending on A, B, and C. You can have 2 roots, lambda 1 and lambda 2. So when I say roots, I mean when you plug them in for lambda in this, you get 0. This equation is true. So you can get 2 roots, 2 different roots, I should say. Distinct roots. So lambda 1 not equal to lambda 2. So let's call that case 1. Case 2, we can get only 1 root. Usually that's called repeated roots. Maybe I'll say, if you took lambda 1 and lambda 2, they're in fact equal. So it's called repeated roots because of what happens algebraically. it's what happens when this left-hand side is a square. So it's like, a linear polynomial in lambda, like alpha lambda plus beta squared equals 0. So this left side factors like this as a square. Then you say repeated roots. So it's like the same root came up twice. Okay, and the third possibility. Okay, so the way I described it when I was making those plots, when I was thinking about okay, so here's the drawing. If the horizontal axis is the lambda axis, then you can have two distinct roots, maybe like that. So these two distinct repeated roots, like that. And then there's one that looks like it should be no roots, right? So just there's no values of lambda that make it 0. And if we call it that, which I'm not going to, I'm about to change it. So this is not how I'm going to describe this case, but let's temporarily say no roots. Then what would we say? Well, okay, so in possibility number 1, if we get two distinct roots, then we have found two different solutions to the differential equation. So that's pretty cool. We would have two different solutions. E to the lambda 1t and e to the lambda 2t would be two different solutions. In the second case, we got one solution at least, e to the lambda t, where lambda is either lambda 1 or lambda 2. They're the same thing. In the no roots case, it sounds like, well, the guess was bad, I guess. We got no solutions. This cannot be solved. The thing that lambda must do in order for this to be a solution is an impossible demand that lambda can never achieve. And so there simply isn't a solution of the form e to the lambda t. That was a bad guess. However, instead of treating it that way, we will introduce complex numbers. So I'm going to call this case complex roots. And I'll say, in that case, we always get distinct roots that are complex conjugates. Alpha plus beta I, where I is the imaginary unit, and alpha minus beta I, for some real alpha and beta. So this kind of picture, this plot, does not capture what's going on in that situation because I'm allowing for complex numbers. And so this is sort of a low-dimensional picture. It's only allowing for real parts. Okay, so we do away with this way of visualizing the idea of roots, and we allow for complex roots. So this means we're going to need to review complex numbers a little bit. Specifically, we'll need to understand not only how complex numbers can be roots of polynomials, but we need to understand what it means for the lambda in the exponential here to be complex. What does it mean to have an e to a complex number? So what in the world is e to the I? And what happens when you take the derivative of something like that? It's showing up in differential equations. So like if I have e to the it, then what is that? Do I follow the usual rules of derivatives? It turns out yes, but that deserves comment to see that it works. All right, so this is a kind of outline of what we're doing this week. We're studying this type of differential equation. The method to solve it is always to make this exact guess here, and then plug in your guess into the differential equation and see what condition it places on lambda. You will always get a quadratic polynomial, and from there are three possibilities as to the roots of that quadratic polynomial. And depending on which of the three cases you end up in, you can get different behaviors. You can get different dynamics in the end. And that So that doesn't tell you quite how to write the general solution. So that's kind of, that question is still left open, and we're about to discuss that soon. So this tells you, once you learn how to analyze each of the possibilities, so for example, possibility 1, that's a pretty straightforward one. In possibility 1, e to the lambda 1t and e to the lambda 2t are solutions. So you would have found two solutions. But we are still left wondering, what's the general solution? Meaning the solution that has these parameters in it so that I can try to satisfy any initial value problem. So we're still left wondering, what's the general solution? And as I dig into each case, we'll discuss how to get the general solution also. Okay, so in the next video, we will dig into case 1, when you have two distinct roots. We will look at how you get the general solution in that situation.